going to talk about an agent-based force vector model of social interaction. First thing is, why are we doing this research? Well, today, social polarization is endemic. And the question we have is, can social dynamics be understood in terms of the attributes of the individuals in a society? This is necessary if an agent-based model is going to work. Can a physics-based model shed some light on the polarization of social attitudes we see today? Can a physics-based model help us understand the changes in social attitudes through wars, pandemics, dictators, environmental disasters, etc.? Can this model help us as a society deal better with polarization? As an aside, I have to say this has been a very fun and insightful project for us. Here's an overview of the model. The agents exist in a vector space whose coordinates are the attributes, the key variables that determine their behavior in this simulation. These attributes might be political ideology or other attitudes, characteristics. In each iteration, all agents interact with each other. There are tens of thousands of iterations in a simulation. And the interaction between agents is modeled as a force. Interactions between similar agents result in an attractive force that causes the agents to move closer to each other. Interactions between very different agents result in repulsive forces that cause the agents to move farther apart. Agents that are very similar merge and form groups, and groups that are very similar merge to form larger groups. We have a vector representation of agents. The agents are in a vector space with coordinates that correspond to their attributes that determine their social behavior. For agent A, the coordinates are XAYA, and they go from the origin to XAYA. For the visible universe, XAYA are from -100 to +100. There are no limits for agent locations during a simulation. The difference in attributes between two agents A and B is indicated by the distance, R, in attribute space between these agents. And R is just given by a Euclidean metric. If R is bigger than an adjustable constant, AIB, where AIB is the allowed interaction distance, then those agents cannot interact. So they must be closer than AIB for them to interact. The forces between the agents are given by this equation. The force of A on B equals a constant times the mass of agent A times the dot product of the vectors divided by R squared, the distance between them squared, times a unit vector in the R direction. The sign of the force is determined by the dot product, AB cosine omega, which is positive if omega is less than 90 degrees, meaning the two vectors point roughly in the same direction. This illustrates the forces between agents. Here's the vector for agent A going from the origin to XAYA, vector for B going from the origin to XBYB. R is the distance between them. In this case, omega is less than 90 degrees. So F of A and B points in the positive R direction and tends to make the vectors closer to one another. In this case, omega is bigger than 90 degrees. And so F of A on B is negative or repulsive. The change in vector B is obtained using Newton's laws. Delta B is equal to the force of A on B divided by the mass of B times a time interval squared. The value of dt is chosen automatically so that the magnitude of delta B is less than a very small value, pre-assigned value. The default is 0.2. So it's a barely perceptible movement in the simulation. This ensures that the simulation proceeds smoothly in a nice rate. The change in vector B is from B to B plus delta B. The same case as we considered before, f of A on B is positive in this case, so delta B lies along f of A and B, making B move closer to A. For the repulsive case, f of A and B is in this direction, delta B tends to move B away from A. Nearly identical agents are merged to form a group. They're less than 0.2 apart, they emerge to form a group. Two groups are merged also if they are less than 0.2 apart. Groups act like individual agents, but they have a mass equal to the sum of the masses of the agents forming a group. Circles represent individual agents in a simulation. Mass is shown below the circle. Triangles represent groups, and the mass is shown below the triangle. Standard initial conditions that we use often: 100 agents in the visible universe, a normal distribution in X and Y centered on the origin, normal distribution of mass. And then we have to pick a value of the AIB, the maximum interaction distance. Here's a simulation with a small interaction distance. AIB is 30. So if agents are more than 30 apart, they cannot communicate. Here, for example, is an agent that is farther than 30, and so it does not interact. You'll see other cases where here's an individual and a group merging. Here are three groups merging, 4 groups, 2 more groups, and you'll see how the mass increases as they merge. This is a typical final state for a case when you have a low, kind of low interaction distance. We have 4 groups arranged approximately symmetrically around the origin. This group here, for example, the coordinates of the group are approximately equal to the average of the coordinates of all the members of this group, which are in this watershed. This is true of all these groups. They are approximately representative groups in attribute space. These groups are so far apart they no longer interacted. Now we can look at a simulation with a much larger interaction distance, 180. So this extends across almost the entire distance here. This agent now is close enough so it can interact with other groups. Here we see 3 groups merging to form a larger group. Here is a group and an individual agent merging. You can see the paths left by the trajectories of the groups as they merge and move. Now we're going to enter a slightly new phase of this simulation. 3 groups separated by 120 degrees. So all forces are repulsive. The force between these 2 is repulsive, between these 2 is repulsive. And the groups are essentially just driving one another as far apart as possible. Strong polarization. This group here, for example, the attributes of this group are vastly different from the attributes of the members of that group. So this shows very strong group polarization. Why did the simulation stop? Because this distance is 180, and beyond that, they do not interact. So what are some of the insights from the model? First, we see that the degree of polarization is directly proportional to the interaction distance, the maximum interaction distance, AIB. The greater the connectivity of the agents, the greater the polarization. Another thing that our analysis has shown is that the number of groups at the end of a simulation decreases exponentially with the interaction distance. How do these insights play out in a larger scenario? Each society has its own attributes, so the specifics of polarization will differ. Some attributes may be common over all societies. Today, with the internet, the maximum interaction distance is effectively global. So our model predicts very strong polarization. Here's a reference for this vector force model. We recently published a paper in PLOS ONE. We have done over 350,000 simulations. The NetLogo model software is available on the web. We are constantly developing new features and open to collaboration. So thank you very much for your attention.